Welcome to Aksharashala. In this session, I'm going to give brief introduction to VLSI design. VLSI design is a technique or methodology to design the layout or footprint of an integrated circuit. It is a multidisciplinary field which involves understanding of semiconductor device physics, knowledge of circuit design, concept of analog and digital logic design, algorithms, and familiarity of electronic design automation tools, that is EDA tools. This course has been developed to provide a comprehensive coverage of the basic concepts and methodologies of VLSI design. The first unit is all about building up of your own CMOS chip. First unit starts with introducing various MOS technologies. MOS technologies are required to implement various digital and analog circuits. And this unit ends with the fabrication process of integrated circuits, and rest of the units helps us to build a good CMOS chip in terms of lower power, area, speed, and cost. All the best, my dear students. Do you think that it's easier to design a mobile phone with a microcontroller or DSP processor or wireless controller? I think it's not absolutely easier to design with those controllers. Then what is the exact solution? Who makes it all? What makes it all? The answer is none other than VLSI. VLSI stands for Very Large Scale Integration. It involves packing more and more logic devices into smaller and smaller areas. VLSI is the process of placing thousands, or we can even go with hundreds of thousands of electronic components on a single chip. Nowadays, VLSI circuits are everywhere. For example, computer, smart car parts, sensors, digital camera, cell phone, etc. All these are VLSI devices. So VLSI technology has been the enabler for advancement of the present electronics and communication years. Silicon has been a natural choice of material for integrated circuit manufacturing. Almost 90% of the electronic circuits are fabricated worldwide are made of silicon using CMOS technology. CMOS technology is the most popular technology because of its lower power and less area requirement. Later, we will come to know more about CMOS technology. All the group 4A elements such as carbon, silicon, germanium, and tin. Tin Latin name is stannum. Exhibit properties of semiconductors. Among all these, silicon and germanium are widely used for the fabrication of integrated circuits. If we add donor impurities or pentavalent atoms such as 50A group elements like antimony, phosphorus, and arsenic, then pure semiconductor will become intrinsic semiconductor, and it is called as N-type semiconductor. So here doping is done just to increase the number of free electrons in case of N-type semiconductor. Acceptor atoms or trivalent atoms are such as 30A group elements like boron, gallium, and indium are used for doping of pure semiconductor to convert it into P-type semiconductor. Now let us see why silicon is preferred over germanium. Silicon devices can operate up to 150 degrees Celsius as compared to 100 degrees Celsius for germanium. Silicon is second most abundant element on earth crust. First most abundant element is oxygen. Germanium is difficult to dope as compared to silicon. Silicon grows a stable oxide, silicon oxide, which is important in the fabrication of ICs as compared to germanium oxide, which is not suitable for device application. VLSI is an acronym and stands for Very Large Scale Integration. A VLSI contains more than a million means 10 to the power of 6 switching devices or logic gates. Early in the first decade of the 21st century, the actual number of transistors has exceeded billion. Billion means 1000 millions, 10 to the power of 9 components. A piece of silicon is typically about 1 centimeter on a side. In 1958, Jack Kilby, who was then an engineer in Texas Instruments, successfully developed the first integrated circuit with 2 transistors, a capacitor and 3 resistors connected together using fine platinum wires. About a year later, in 1959, Dr. Robert Noyce from a Fairchild camera is also one of the co-founders of Intel Corporation, invented independently his own integrated circuit chip. This is the Jack Kilby IC. Both Kilby and Noyce shared the patent right for the invention of the integrated circuit. In 2000, Kilby was awarded the Nobel Prize in Physics for his part in the invention of the integration circuit. The JK flip-flop was named after Jack Kilby. The modified RS flip-flop circuit that eliminates race around conditions was named JK flip-flop in his honor. He died of cancer on June 20, 2005 at the age of 81 in Dallas, Texas State, USA. First planar IC or monolithic IC was built in 1961. Here, planar refers to manufacturing process used in the semiconductor industry to build individual components of a transistor and in turn connect those transistors together. A monolithic IC is one in which all circuit components and their interconnections are formed on a single thin wafer called substrate. In 2003, Intel Pentium 4 processor is fabricated by using 55 million transistors. 512 megabit dynamic RAM is fabricated using more than 0.5 billion transistors. 53% of compound annual growth rate over 45 years for this VLSI technology. No other technology has grown so fast so long. VLSI technology is driven by miniaturization of transistors. So transistors now fabricated at a very small size, and if you go for mass production, cost automatically comes down. So these circuits are very faster and consumes very less power. So this VLSI technology brought revolutionary effects in the society. Before 70s, all circuits were implemented with PMOS transistors. So this PMOS technology suffered with lower speed and leakage currents. In 70s, all circuits were implemented using NMOS transistors. This NMOS technology is inexpensive, faster, but consumes power while ideal state. From 1980s to present, we are using CMOS processes, which is a combination of both PMOS and NMOS technology for ideal low power and area. This is Intel 1101 256-bit static RAM, and this is first Intel 4004 4-bit microprocessor. Moore's law. Gordon Moore proposed one law in before 1970s itself. In 1958, Jack Gilby built the first integrated circuit with two transistors at Texas Instruments. In 2008, Intel's Titanium microprocessor contained more than 2 billion transistors, and a 16 GB flash memory contained more than 4 billion transistors. This corresponds to a compound annual growth rate of 53% over 50 years. No other technology in history has sustained such a high growth rate lasting for so long. This incredible growth has come from steady miniaturization of transistors and improvements in manufacturing process. Gordon Moore is a co-founder of Intel Corporation, visualized in the 1970s that chip building technology would improve very quickly. He projected that the number of transistors on a chip would double about every 18 months. Moore's law. The integrated circuit was only 6 years old in 1965 when Gordon Moore articulated Moore's law, the principle that would guide microchip development from that point forward. In 1965, Gordon Moore plotted transistor on each chip. So here, if you see this plot, as years increases, the number of components that are integrated over a single chip also increased. It is a exponential increasing. The number of transistors per chip double for every 18 months. This is called Moore's law. Then, why VLSI? What is the purpose of, what is the use of VLSI? So nowadays, VLSI circuits, VLSI devices are used everywhere. So these are used in entertainment field, clean energy and communications. These are used in tablets, computers, in sensors, in cars, military systems, in healthcare systems, and many more. In almost all fields, VLSI devices are used nowadays. Here we are integrating all the devices over a single chip. This integration improves the design. So it consumes very less power. So automatically size also drastically decreases. So one more is lower parasitics, higher speed. So here parasitic means there is always a non-zero capacitance between any two conductors. This can be significant at higher frequencies with closely spaced conductors such as wires or PCB traces. Similarly, unwanted capacitances exist between the terminals of transistor. This is unavoidable and usually unwanted capacitance that exist between the parts of an electronic equipment simply because of their proximity to each other. This is called parasitic capacitance or stray capacitance or self-capacitance. If this parasitic capacitance is low, from this equation we know that I equivalent Q by T, no? So Q equivalent CV. So from these two equations we can write I equivalent CV by T, where T is propagation time, where T equivalent CV by I. So if C is high, I is low, then what happens? Propagation delay increases. So to keep, if T increases with increasing capacitance, hence parasitic capacitance should be low to keep propagation delay less. If propagation delay is less, it leads to higher speed. So propagation delay is less means circuit will be faster, which leads to higher speed. Major advantages of IC over discrete component based circuits. So if you implement a circuit using discrete components, there are so many disadvantages. Size increases, speed decreases, power consumption will be more. So if you implement by using IC, these are the advantages. Size drastically decreases, speed increases, power consumption decreases, cost also reduces as we are going for mass production. More functionality and reliability also increases. So there are some few disadvantages. Design complexity will be more. Long design means fabrication time will be more. It takes more than 3 years for fabrication of a single IC. VLSI applications. VLSI is an implementation technology for electronic circuitry, whether it may be analog device or digital device. It is concerned with forming a pattern of interconnected switches and gates on the surface of a crystal of semiconductor. VLSI is used for fabricating microprocessors, personal computers, microcontrollers, memory units like dynamic RAM, static RAM, special purpose processors like application specific integrated circuits, optical switches. VLSI has made highly sophisticated control systems. When these VLSI systems are produced in a massive, produced in a in a huge manner, then automatically cost comes down. What is a silicon chip? A pattern of interconnected switches and gates on the surface of a crystal of semiconductor. These switches and gates are made up of areas of N-type silicon, means N-type transistors, areas of P-type silicon, PMOS transistors, areas of insulator like SiO2. SiO2 has excellent insulator properties to separate the conductors, and lines of conductor. These are used, and these are also called as interconnects, and are used to provide communication between various transistors. For aluminum, copper, titanium, molybdenum, polysilicon, tungsten, this type of elements are used as interconnects. The geometry of these areas, how these all these components are laid over a single chip. So this geometry of these areas is known as where N-type transistor is kept, where P-type transistor we have to keep. How to separate these two transistors with the help of insulator, where to keep insulator, how to provide connection. This is called geometry or layout of the chip. So this geometry of these areas is known as the layout of the chip. Connections from the chip to the outside world are made around the edge of the chip to facilitate connections to other devices. Digital components is largely composed of switches. Switches can be built from many technologies, relays from which the earliest computers were built, thermionic valves, transistors. The perfect digital switch would have the following: switch instantly. Perfect switch doesn't exist. If it switches instantly, then that is called perfect digital switch, which doesn't use any static power, which offers infinite resistance when it is in off state and offers zero resistance when it is in on state. Real switches are not like this. Real switches and practical switches offer more resistance when it is off and less resistance when it is in on state. This lists the various levels of integration. The main target of IC design and fabrication is to achieve more functionality at higher speed using less power, less area and low cost. This table lists the different IC technologies that have evolved over the 50 years. Based on components density of integration, the levels of integration are as follows. Integration level. Small scale integration. So in this integration, so this is used in 1950s. In this integration, components more than 10 and less than 100 components are used to fabricate circuits. This integration is called small scale integration. Medium scale integration, MSI, is used in 1960s. In this integration, components are in between 100 to 1000. In large scale integration, which is implemented in 1970s, and it uses components in between 1000 to 10,000. VLSI, in this integration, which is implemented in 1980s, in this components used are in between 10,000 to 1 lakh. VLSI, ultra large scale integration, this is used in it is implemented in 1990s. This technology uses components more than lakh and less than 10 lakhs. A super large scale integration, which is implemented in 2000, more than 10 to the power of 7 components are used in super large scale integration. Nowadays we are using giga scale integration. it is more than 10 to the power of 9 components are integrated over a single chip. These are the various levels of integration. By using SSI, logic gates like AND, OR, NAND, NOR gates are implemented. By using medium scale integration, flip-flops, adders, counters, multiplexer, demultiplexer, such type of circuits are implemented by using medium scale integration. By using large scale integration, small memory chips, programmable logic devices are implemented in 1970s using large scale integration. By using VLSI, large memory chips like complex programmable logic devices are implemented by using VLSI technology in 1980s. In 1990s, by using ULSI, 8-bit and 16-bit microprocessor are implemented. In 2000, by using SLSI, advanced microprocessor started implementing using SLSI. Now present by using GSI, all the present latest 10th generation, 5th generation microprocessors are implemented by using the latest GSI technology. VLSI is an integration level here. Types of integrated circuits. Depending on the types of substrates, devices, signal processing and applications, ICs are classified as bipolar ICs, CMOS ICs, BiCMOS ICs, MESFET ICs, HBT ICs and HEMT ICs. In bipolar ICs, bipolar junction transistors, BJTs are used to implement the integrated circuit. In CMOS ICs, combination of NMOS and PMOS transistors are used to implement the integrated circuit. In BiCMOS ICs, combination of BJT and CMOS transistors are used. MESFET, metal semiconductor field effect transistors are used in these MESFET ICs. HBT ICs, these ICs use heterojunction bipolar transistors for the to implement the integrated circuit. HEMT, high electron mobility transistors are used in these ICs to implement the integrated circuit. Design methodology. Design methodology. VLSI design is a sequential process of generating the physical layout of an IC starting from the specification of that circuit. It can be fully or semi-automated using numerous softwares called electronic design automation (EDA) tools or computer-aided design CAD tools. The designers first get an idea of a new system or a device for a particular application. This new idea is translated in the form of an integrated circuit chip using the VLSI design flow. So in next class we will discuss about VLSI design flow. Thank you. Please, for further updates, please subscribe to Aksharshala.